So we're back and going to continue working on something that we were doing yesterday. So we're building a cipher mode for AES, and we're using an algorithm called, or a specification for an algorithm called GCM, AES-GCM. And I'm a newbie when it comes to crypto, and a relative newbie when it comes to AES and Rust, particularly Rust. So, anyway, so we're going to continue doing what we were doing yesterday. If you join the chat, please say hello. Don't be shy. What I'm going to do is kind of just recap what we were doing yesterday. So, what are we doing here? So we've got a single module here called AES-GCM. At the moment, we're just kind of going through the specs available on the NIST.gov, the NIST website, and we're going through and we're sort of understanding it, making sure we're building it appropriately. We've built two of the algorithms so far. We've got the multiplication algorithm on blocks. We've got the G-hash algorithm, and we've now started to build the GCTR algorithm as well. Or function, I should say. So this is going to be, this is kind of where we're up to. So we're doing a lot of bitwise kind of operations on 128-bit blocks. It kind of that defines the mode of operation. Or at least AES operates on 128-bit blocks, and so this actual this mode of operation takes those blocks and kind of applies the cipher to them and joins them together using a block counter and XORing them together. At least that's the component that we're working on right now. And then the authenticated encryption part does more than that. Uses that hash algorithm, but then uses the hash algorithm we created, uses the GCTR algorithm, and then also computes a tag for the authenticated additional data. So if you want to understand a little bit more about this, look at the video from yesterday. Just see if I can see. Yeah. Okay. Let's have a look at something here. Great. So anyway, and so if you're not familiar with Rust, it's a compiled language. It's awesome. It's fast. It executes very quickly. Sort of executes as quickly as most good native compilers do, like C and C++. The compiler is interesting because it gives you higher level primitives. In fact, I mean, the syntax looks reasonably complex, perhaps, but when you get into writing it, it feels a lot more like a high level language. Like Python, perhaps. I hesitate to say Ruby. It certainly doesn't feel like Ruby, but there are functional aspects to this. It's kind of it's possible to write Rust in a number of different paradigms. I wouldn't call it object-oriented, but it certainly allows you to start encapsulating your data in structs and applying methods to those structs and building very similar types of concepts. It's also able to, you can write it in a fairly low level way. So, in the case of writing crypto, we want access to strongly typed low level primitives like, we're building things that operate on bits in 128-bit blocks here. And this would be quite familiar to C programmers, perhaps. Anyway, I'm enjoying it. And more importantly, the ergonomics of the thing. So if you look at how I run this, it's just cargo run. Or if I've got unit tests, I just do cargo test. And all my tests are down here. I've got a module here called tests. They contain everything that I want to test, and it just runs all the functions, and cargo run gives me a way to run that test harness. Or it gives me a test harness to run my test suite. Anyway, and so at the moment I haven't really turned this into a library. It's just a main program. It does very little, and I'm kind of relying on the tests to drive all the functionality. In fact, we'll probably build the majority of the code this way until we're ready to test it and use it in anger, in which case we'll probably then pull this into a library and have a separate binary that uses the library. Anyway, so what we're going to continue through today is really going to dive into this GCTR function. Now the approved cipher we're using is AES-128. I've built that previously. That's my only dependency so far, and that's the link to my AES crypto library in GitHub. So I'm able to import that and use it. You should see a use statement here somewhere. Maybe not. Yeah, I'm not using it yet. Or am I? No, okay, here we are. So this is, I mean, I'm not importing the library, but I'm using it directly here. And so this is for example, this takes, cipher should take some plain text and a key schedule and generate ciphertext, which I think is correct here. Yeah, so it generates 16 bytes, 128 bits. And in this algorithm, excuse me, the way that is supposed to work, I'm jumping around here, but the way that's supposed to work is you're meant to build a hash sub key, and then on the 0 block, which is what this is doing, I'm faking the key schedule right now. The key schedule should be generated from a real key. In fact, that is something that's available in the library. So let's have a look. Expand key. So expand key is takes input key material and then generates a list of U32, which is effectively what we're faking here. Anyway, and so I won't go through that here. We will be doing that at some point. I've got my mic in the worst possible place. All right. Anyway, and so so we started diving into this kind of core authenticated encryption algorithm, and it's pretty clear that I guess that potentially should work, but then we're going to very quickly need to implement GCTR, which is defined here. So I don't know, maybe we just do top down like that from the calling function, GCME. So yeah, anyway, and so right now I've got a counter block, some ciphertext, and I call GCTR on that. Plain text being the thing that I want to encrypt that's passed in. It's just a list, an array of bytes. Ciphertext is basically the encrypted bytes that we'll want to get our hands on afterwards. So yeah, so you can see that's not quite right. We haven't implemented the inc function, the increment function, which we'll need to do. So anyway, we're missing bits. And we also need this initialization vector too. So the initialization vector needs to be a randomized thing. The other thing that I started showing yesterday was that I've found some test vectors here. And these are, including the IV, the key, contains everything and all these different permutations. There's literally, thousands of these things. And in fact, one of the tests that I wanted to try was using this block of data. So what we could actually do is start using this. So at the very least, we could just do something like let key. So let key equal this. But key needs to be a list of bytes. So I could probably just do this, suspect, but that won't work either. That'll give me a list of bytes, but it won't be what I expect. Be treating this as that's a byte. Yeah, okay. So Rust byte literal. Let's have a look. Byte and byte string literals. So I guess we could try this. Starts with X, a byte escape. It denotes the byte equal to the. So, I wonder if that works. 34, that's clearly not right. Let's have a look. What's that? 4. It's a shame. Really don't want to do this. But I guess I can. I have to. There's got to be a faster way. Do like a Rust byte string in hex. Yes, I don't have to do that. From hex. Hex from hex. Hex from hex. Excuse me. So that's the kind of thing we want. vec from hex. Expect couldn't pass hex. Use hex from hex, and then these are only test dependencies. I think I should be able to do that. Don't know. Rust test dependencies. Test only. Dev. Alright, let's try that. Hex cargo. Dev. Try this. From hex. It's a vector now, I guess. Anyway, we'll try this. So let iv equal vec from hex. Expect couldn't parse hex. Let ct equal vec from hex. Couldn't parse hex. I mean, we should be saying things like couldn't parse key or something like that. Initialization vector CT. So that's ciphertext. From hex. Expect couldn't parse authenticated. I'll just stay to AAD. Let tag from couldn't parse tag. Let vec from hex. Plain text. Parse plain text. All right. So now we've got these. We're using a new library, but that's fine. And we've got these new values, which are just vectors. Type error. It's weird. It doesn't like it. Cargo test. Seems to be okay. Well, so let's have a look. Decode hex string intermutable byte slice. That's what I needed. Excuse me. Hex decode to slice. Anyway, should just be able to do slices here anyway, I think. Anyway, and then we're going to call our main function, which is GCM AE. Ciphertext and tag need to be mutable. Tag. Actually, that's fine. So GCM. Whoa. Let's do GCM AD. Right. So this is where we need I guess it's IV. I wonder if this won't work, will it? Anyway, we'll work it out. Ciphertext CT. So the CT, additional data, the AD, tag will need to be empty. So we'll need a computer tag. We'll do test tag. Which is just going to be a reference to a list of things. But we don't know how long the tag is, do we? Do we? Don't think we do. We can make it a vector of bytes. This is all wrong, but it's fine for now. Let mute ciphertext test CT be the same thing. Plain text. It's just going to be PT. Okay. Excuse me. Okay, and it returns an enumeration. Okay. So we we'll actually match on this, right? So we're not going to just assign it to a variable. We'll match. It's enumeration. We can destructure it in Rust. So we can do like a match and then look for whether it's a pass or fail. Which is pretty cool. So we do something like this. We just call match on the whole thing. And then it's, you know, authenticity pass, we do something. And then if it's authenticity fail, we do something else. Like that, which was nice. But PT, plain text needs to be immutable apparently. Doesn't make any sense, does it? Oh, I've got it totally wrong. IV, plain text. What? That's really annoying. I thought it was ciphertext. Oh, geez, I'm doing encryption here. Oops, mistake. All right, so it's the initialization vector, then it's plain text, then it's additional data. Okay. So it's ciphertext here, plain text. Ciphertext doesn't, yeah, ciphertext does need to be immutable. Well, it's not that anyway, is it? It's test CT. Then additional data needs to be immutable. Does, oh no, it doesn't. Tag does. Okay, good. All right, so I think we've got our calling function here. And so this thing should fail. I mean, it should do something, like it should compile. So now we run a test. But what we need to test, of course, is that whatever we get back here is so we need to test that ciphertext and tag come out right. So that's easy. So we can just do, for now, print line, ciphertext. And then we'll just do whatever ciphertext is. Sorry, it'll be test ciphertext, won't it? But I guess a reference to it. And we'll just do debug. Okay, and then we'll look for the tag as well, which will be test tag. Okay, easy. So what we'll do is we'll assert false. use a macro. So we're going to assert that whatever we get back in test, we're going to assert that it's equal. But whatever we get back in test is, I guess, CT. But this will be, can I compare vec with, no. Something like that, I think. And then we'll do the same for tag. That should fail. Nice. So we're getting bytes. So the first one fails, which is what you would expect because we're not actually doing anything. The next one should fail too. It's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the tag should be 15 bytes. Column 34, 63, 64, yeah. Okay. So 30, yep, 15. Great. All right. So that's good. All right, so now we have a failing test that we can make work. Key. Ah, key's not used. That's true, it's not used. Right, so we need to work out what this process looks like. Because we don't need the key. So let's look at it. In step 1, the hash subkey for the G hash is generated by applying the block cipher to the 0 block. In step 2, the pre-counter block J0 is generated from the IV. When the IV is 96 bits, then the padding string is appended. So we basically put 32 bits on the end of it to make it 128 bits. With zeros and then a 1 to form the pre-counter block. Otherwise, the IV is padded with a minimum number of 0 bits, possibly none, so the length of the is multiple of. Okay, we're going to do padding again. That'll be fine. So we need to pad IV. So I actually need a pad IV type function, won't we? Check if, well, pad IV if needed. I mean, we could do a check here, couldn't we? So we could say, well, where is IV? It's coming in. So if the length of IV isn't, this is going to be in bytes. Okay, isn't a multiple of 16, then pad it. Doesn't equal 0. Pad if needed, if IV isn't a multiple of 128 bits. And it almost never will be. So we'll do I've been making this choice to kind of internally convert all the bytes to unsigned 128-bit ints. And I'm not sure if that's the right decision. It makes some of the arithmetic and some of the other stuff simpler. So it's kind of like the interface, all the inputs are bytes, and then internally I'm doing 128-bit. But then I wonder if I should be outputting bytes again, probably. Not sure yet. Anyway, and so what we'll need to do here is we'll need to pad IV, and we'll pass obviously a reference to IV. And I don't think we'll make it mutable. We could, but let's generate a new IV. All right. So this assumes, yeah. Yeah, so this thing, oh God. Anyway, let's just do it this way. Let padded IV equal pad IV. This thing assumes we get exactly 16 bytes, which is probably not right. Anyway, so we'll create a new function here called pad IV. It'll take, you know, a list of bytes. We'll just call those bytes, I guess. And then it'll return. The question is, do we return a list of do we return a list of U128 or bytes? So how's IV used? So the initialization vector is only used to construct J. God, I'm trying to find some decent music to play here. Bit of Tame Impala. All right. Make this a little bit bigger. Right. So you can see how it generates the tag. Takes this initialization vector, generates the J0 block, calls increment on it, passes that into GCTR. Padded bytes or padded IV. So yeah, not sure of that yet. So we'll need a padded IV thing, which will be, I don't know, maybe a list, won't it? Padded IV. Will be a vector of U128. So don't need that. And we should be doing checking, error handling. We're not doing anything. Yeah, so the IV is only used there. It only needs to be padded once. A lot of the work happens here. All right. Okay. G hash has placed the resulting string to form the pre-counter block. Okay. Build the pre-counter block. Then add blah blah. Okay. So this gives us a counter block. The counter block could be, actually, what is it? Oh, counter block will always be, so it'll come out of G hash, which we built here, which returns a single U128. Okay, cool. Well, that's all right. So IV. Hash subkey is not used here. What the? Oh, yes, it is. Okay. So G hash is called. That's the hash subkey. Right. So yeah, so we've already made the assumption that it's internally 128-bit. So we'll just keep it like that. Returns our hash. Okay. That's fine. We'll assume that this does all the logic, including, appending with 64 additional 0 bits and 64-bit representation, blah. Resulting string. Yeah, see, that's interesting. So, could be quite long, couldn't it? So this will be a total of 128 bits. So it'll be at least 256, or whatever this is, plus 128. And G hash takes okay, cool. Well, that works. Okay, well, in that case, let's do this. It makes it a bit easier, doesn't it? So we'll just do padded IV, push, push, and it'll just be like this, but then it'll be ORed with the length in. ORed with IV length as U64. Sorry, as 128. I think. I mean, this should give us the right thing. I'll check this. So to do. Lots of to-dos. Does we need 0 64 times with IV length as 64-bit. How do I represent that? Like 64, something like that. Bits. So we need to concatenate 64 bits or 64 zeros and IV length as a 64-bit representation. And then we apply the G hash to that, which gets us a counter block. So that's, G hash of whatever the hash key is, which will be hash subkey, and then this padded IV thing. This will now be wrong. So this will be U128. So it's almost like we want to break that back up into bytes. Just as we had U8 to U128, we want the reverse of that. Right? And check this. Generate the key, is that right? Does that make sense? Counter block, no, I think that does make sense. Okay. So this would arguably give us J0. But we have to all the logic obviously in pad IV. And then we need to call inc. So counter block. Yeah, maybe it could just be U128. Inc 32, but we just still need to inc, don't we? I guess we just do this. Inc s bit string. Yeah. Inc s. So the bit string is J0. S is 32. We need some output. So this is that inc operator. Inc counter block. Inked counter block. But what does it return? Inc was defined up here somewhere. Inc. The output of incrementing the rightmost S bits of the bit string X regarded as the binary representation of an integer by 1 modulo 2 to the power of whatever. So it's 32. So you'd increment the rightmost 32 bits of the bit string by 1 modulo 2 to the 32. I wonder if it actually tells us how that's implemented. A little bit unclear. Inc. Guess. How do I search for that? Oh, there you go. Ah, very cool. Incrementing function. It's not clear that it always operates on, so bit string such that the length of X is greater than S. But is it always 128 bits? I think it is. That's the bit we want to understand. Boy. If you join the chat, feel free, just say hi, introduce yourself, tell us why you are possibly on a channel that's only talking about crypto and Rust. I'm sure you have better things to do. So that's a bit unfortunate, isn't it? I mean, this is more general, but I kind of want to just keep it simple. Is the bit string ever going to be different to 128 bits? I don't think so. Pre-blah. It's because J is always the hash. And the hash always returns 128 bits. Doesn't it? Oh. Could be a multiple of. Really? That's the input. The output is a block. Okay. So it could be really long. I think. Let me just remind myself. So G hash. For 1 in M, let y equal multiply block So mul block always returns. So you're always XORing, yeah. So and mul block always returns 128. So it's always 128, which is good. So inc_s can just operate on a U128. At least that's what I'm going to say for now. And the output should also just always be a U128. So the bit string in our case is just the counter block. And we only want 32 bits, and the output is something else. I guess I could just return it, right? Be easier. And then I could just do inc_s like this. 32, but then it would. So I need to pass it as a reference anyway. GTR. And then this thing can just be that. So this thing can just be modified just to return that, which for now can just be 0, just so we get some working code. This should give us our ciphertext. I think that should be alright. But ghash, something about that doesn't make sense to me. So, yeah, it does. It always returns, because we're always XORing. Yeah, so it's always 128. Nice. Alright, so I think that's kind of the high-level encrypted, the authenticated encryption bit done, with lots of gaps, obviously. Oh no, it's not even close what I'm talking about. All right, so we've got this ciphertext now, presumably, and then we define two variables, u and v. Right, so this is our extra data. These are the number of zeros that we pad with, I guess, or panned. And that goes into a ghash, which gives us 128, which goes back into GCTR again with J0, unincremented J0. Okay, so let's just counter block again. And then the most significant, is that bit or byte? Most significant. The bit string consisting of the leftmost bits of the bit string X. Okay, because it's okay. Right. So MSB, we'll need an MSB function. That's fine. For T, whatever T is. Anyway, application is the ciphertext. In steps 4 and 5, the AD and the ciphertext are each appended with minimum number of 0 bits possibly known, so that the bit length of the resulting string is multiple of the block size. Concatenation of these strings is appended with 64-bit representation of the length of AD and the ciphertext, which is this bit. And the G hash function is applied to the result for a single output block. Yep, and then that's encrypted again. The pre-counter block that was generated, and the result is truncated to the specified tag length. Woohoo! To form the authentication tag is truncated. It's the leftmost bits. The ciphertext and the tag are returned to the output. Nice. Starting to come together. Albeit very slowly. I mean, this is really so complex when you think about what's actually happening here. Kind of does my head in. So I guess, yeah, but what's the original key schedule? That's the thing we don't understand. So we can do all this other stuff. That's, you know, go and compute U and V and, you know, append stuff and hash it and encrypt it again. So I get all that. So this needs to return the ciphertext and the tag, and that'll be there. So but it is mutable. It is. Ciphertext is mutable. Mutable. Dum, 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 dum. Bar is mutable, but it is. Ciphertext is might change the webcam setting here a bit. It's not zoomed at all. And then do that. Tilt it a bit. Okay. Zoom in a bit more. Play it. It's better. All right. What's going on here? Ciphertext is mutable. So it's Ciphertext is a reference to a mutable list of, or is this said as mutable reference? Hang on a sec. It's better. All right. This is awesome though. I love trying to work this stuff out. So we've basically kind of got the boilerplate to get to this point. And then we need to do all this work. We haven't even started to build GCTR. So there's a lot more to do there, which is basically defined here. And to do that, we'll need to implement this MSB function. Yeah, so let's think about I just want to understand where this key is going to come from. So the key is passed. So the input is, so we need to pass a key in. That's missing, right? So it's like we need a key, which is going to be, I don't know, what is the key? How long is the key? Key K. So we use a cipher to generate this hash subkey. It's going to be so complicated to debug. We'll see how. All right. Anyway, so the key is a key schedule. The key schedule needs to be actually created. All right, so let's look at how I did it in my crypt. Oh, want to add it. Go to the crypt library. So add that to my workspace. So you can see it's not a great library. I mean, it works, and I've got some good tests. So this is kind of the driver. This is how it works. So if I assume that I get an array of bytes, which is what I will have, and then basically I'll do expand key, and that will give me a key schedule. Key length, right. How's key length defined? So what's my key down here? Key. So we've got 16 bytes. Anyway, so we go back here. We assume by the looks here that it's 128-bit key, which is kind of it's an enumeration inside of the module. I really need to clean up this interface. This isn't the nicest way, I think, to expose this stuff. But anyway, and then we've got a key. We generate So the key schedule is basically a list of these 32-bit numbers, 32-bit things, and there's 44 of them. And then we pass that into expand key, which generates a key schedule. And then we use that when we call the cipher. So we do that per block. And then let's just remind ourselves here. So then for every round, yeah, it mixes all the keys up and uses a different key. Let's add round key do again. Mixes in the key material with state. Wow, yeah, anyway, generates a whole bunch of mixed up nonsense. Anyway, and so we will need to do the same. So we're sort of cheating here. We actually need to take the key, which is something we've completely forgotten. So the key is going to be an array of bytes. Which is fine. So this thing needs to pass in the key. What is it? Key? Cool. So are we using everything now? I think so. And then the key will be used. So create that. If you look back at how I was driving it, so I did something similar, right? I built this list because I knew how big it needed to be. But I also need to assert probably yeah. I think I'm going to ignore this stuff for now, and then I'll add it into the library later. It's probably something I can do when I'm building. All right. Anyway, enough of that. Oh, what have I broken here? All right, because this thing needs key too. And key in this case was going to be a key schedule, I think. Yeah, must be. Which is a which is U3244. Call it key schedule. And it's going to be a reference to all this goodness. And so that will be just a reference to key schedule. It's all starting to come together, isn't it? Key schedule, I guess, do you just generate the key schedule? Do you generate it once? Or do you have to do it every time? I mean, does it even make sense? Well, anyway, and what we're going to have to do is call expand key, which takes the key and builds the schedule and blah, blah, blah. This has to be, what's expand key expect? Oh, key length. Great. That's all right. We'll just steal this. Which doesn't exist. So we'll just call it specifically like this for now. And the key length, I'll just do, I'll just hard code it for now, which will be key length of 128. This needs to be mutable. Okay, so this gets a key. So we'll build key schedule for Cypher. And then we apply that to the 0 block. And then once we've got the key schedule, I think we could just keep using it. I think. Great. So it runs, but obviously the test fails. Okay, I feel much better about that now. Now I know what. Now I've got a key. I mean, technically we should probably be checking, but I guess. All right. So tag doesn't get written. Additional data doesn't get read yet. That's okay. It will. Awesome. It's starting to come together, isn't it, guys and girls? All right, so I'm going to take a small break here. I think we've been going for a while. Don't know how long, but it's been a while. And then I'll come back and do a little bit more. So hang around. If you join while I'm on a break, you know, I'll be back. So don't go anywhere. All right, back. So what I'm going to do, excuse me, is I'll probably just play around with some of the auxiliary functions that we need, like MSB and LSB and inc, and maybe implement a couple of those. So we've got the overarching structure kind of put together. I mean, I could complete that, couldn't I? And sort of get the top-down structure done. IV is padded with minimum. The IVs. And the same key. Okay. So IV needs to be unique every time. Wow. And then okay. Any GCM key that is established needs to be fresh. I guess, I mean, you could... GCM keys may be established using the key. So, to build IVs, yeah, deterministic. Oh, so it talks about how to build the IV and how many times you can invoke authenticated encryption. Lots more to learn about this. So this is actually quite involved, isn't it? Like, I thought building AES was involved, and it sort of was. It took me, I think it took me like a week or so. Maybe, can't remember. It took me a while anyway. But this is more involved in a different way. And I can see lots of edge cases where you absolutely have to nail it and get it right. Otherwise you'd be in trouble. All right. Anyway, enough procrastination. Need to dive in and do some of this, don't I? Which bit to do? Incrementing function. Output. The AED and the ciphertext are appended with minimum number of 0 bits. Multiples of the block size. Is that what that means? Guess that means multiples of 128-bit. Oh, what does that notation mean? Product. What to do? What to do? All right, so I reckon we just go and build MSB, and do we need LSB anywhere? It's mentioned. Yeah, it's used for ink. So let's do MSB and LSB. Oh, right. So I actually implemented it for a single bit, I think. LSB. Oh, but that was just for a byte. This is for an arbitrary length string, bit string. Okay. So I actually need... And I don't think I used this anyway, did I? No. Oh, I did. Okay. Well, anyway, I think what I'm going to have to do is change this. And I think it's okay for it to be a bunch of bytes. But then I'll need to also... Okay. Anyway, we're going to have to do number, but what are we going to call it? Like n bits or something? N bits, and that'll be a number. And then it'll have to be bytes, I think. And then the result won't be bool anymore. Okay. So let's just call this all right, let's where's my ink? So we'll do LSBS and MSBS. And then number of bits will be a number, and then we'll take bytes, I guess, as input. What am I doing? U8, and then I guess the result will be a list of bytes. It's gonna be the same signature, really. Result will have to be immutable. So return LSB will be the rightmost n bits in bytes, and then most significant will be the leftmost. So the leftmost n bits in bytes. Get the leftmost. Yeah. Okay. And then inc uses that, doesn't it? Okay. Commits the right, increment the rightmost. This S. Okay, we'll do the same convention. It's terrible though. So this will be S, S, and then S will be first. And then we'll just this. So yeah, so S needs to be, I guess, less than or equal to bit string. Alright, let's have a look at how this is implemented. Well, the output of incrementing the rightmost S bits of the bit string regarded as the binary representation of an integer by modular, right? Bit string by by 1 modulo 2 to the power of S. Bit length length of the bit string. Yeah, I have a feeling that I've been making some errors here, like where I'm calling length. Like that's not right, because you know that'll be in bytes, right? For example, so I'm gonna have heaps of bugs. It's gonna be something like this. To the 64. Yeah, I don't know what the number is. Anyway, where else am I calling length? Implicitly or otherwise? Pad. IV. Oh yeah, so that. I knew that was bytes there, I think. Isn't a multiple of 128 bits, yeah. Okay. Pretty sure that's true, isn't it? GCM AE. GCM AE. Length of IV is 96. Oh, this is wrong as well. Oh no, padding. Oh, that's the padding function that I haven't written yet. Okay. Okay. Where's pad? It's pad. Function pad, where are you? Cool. Pad. I think these are largely useless. I mean, print bits is good. I'll use that. I don't think I need any of this other stuff. Anyway. Okay. Anyway, we'll find those if they exist. So then how do we define LSB? LSB, where are you? Well. So yeah, what was this modulo? By one modulo 2 to the power of 32. Oh, in that case. So, okay. That makes sense. So we never overflow. We leave it, yeah, well, anyway. That's kind of how I assumed that would work. Alright, so MSB, given a bit string X, and a non-negative integer S, such that the length of x equal to s and the functions. So return this s least significant bits. For example, least significant bit of that is those, and that is that. So increment is basically MSB my goodness. So inc s of x is the most significant bits from the length of x minus s of x concatenated with is that the leftmost s bits? Binary representation of the non-negative integer x is a string of s bits. Of s bits. Right, so I guess where x is always less than 2 to the s, right? So you never truncate it, but it could be bigger. Makes sense. So could have leading zeros. Okay, that's all right. So the integer, the s least significant bits of x plus 1 mod 2 to the s. And then as s bits. So this should return 32. Oh, hang on a second. Oh, no. Okay. So it's going to be, yeah, so it's going to be the same length because it's x minus s and then s. So you still get x number of bits. Wow. It's so cool. I have no idea exactly mathematically what this is doing. I'd love to understand it. I think that's the key with crypto, right? It's not just trying to understand the algorithm at a high level. That's relatively straightforward. But then if you actually get into why it's doing this, mathematically why, and have an intuition for that, that's the deeper bit that I'd love to get to. And I don't know how you get to it. I guess you do a course in the mathematics of encryption or something, of cryptography. Mathematics of cryptography. Mathematics in cryptography. Book. What's the best book to read on this stuff? Mathematical cryptography. It's like if you really want to understand it, quantum. Mathematical cryptography. Very cool. Anyway, I'm definitely getting sidetracked now. Looks like some of these are good. Nope. Number theory cryptography. Yeah. Anyway, sidetracked. I think my brain's starting to get tired. Anyway, it's pretty straightforward what all this does and means. As far as, I mean, it's going to be a bit annoying, right? Because this is defined for any arbitrary number of bits, and that just seems inefficient to me. I mean, you'd have to pass around like bytes, and then I don't know the number of bits that are most significant, like a little struct that has a list of bytes and which ones we care about or something. It's just a bit annoying because you don't want to use strings. But then realistically, I don't think we're ever doing anything that's not on a byte boundary. And then, I mean, if you look at how MSB and LSB are implemented, called, let's have a look. So here, it's the length of, okay. So it's, yeah, okay, so if we've got a partial block, then, so that'll still be bytes though, presumably. And then MSB is used down in here, isn't it? T is the tag length required. And then inc is always, 32, always multiples of 8. So it's always, well, I guess tag could be any number of bits, right? Support tag length associated with the key. Tag length associated with the key. Definition of supported input-output lengths. Supported tag length T. Tag length. Yeah. So what is the tag length? If I go back to my example that I had here, tag. So we just had a tag. It didn't tell us. I mean, obviously, the tag length here is 15 bytes. Right, so what's that? 120 bits. Tag. How do you know? Tag length. So tag length. Is the tag length of 120? Oh. Tag in 120. Oh yeah, there is. Okay. So yeah, it's one of these that I was using. So tag length. I guess tag length is that operations, primitives. So for AES-GCM, what tag length works? Ah, it's set. It's defined for a set number of tags. Okay. Oh. Right, so you need to know what tag size. So shouldn't that be passed in here? Right, so these inputs, wherever I was. Right, so tag length needs to be passed to the 12 bytes, 96 bits, yeah. So we'll just do 96 then maybe. And then to transport, how to transport ciphertext. Generally the IV is prefixed to the ciphertext or calculated using some kind of nonce on both sides. And I guess that's, the IV for TLS. Who knows? Who knows? The calculated tag will always be 16 bytes long. GCM is defined for 128, 120, 112, blah. And it's strongly dependent. You should try and use but in general, tag size. So yeah, so who defines the tag size? In TLS. TLS spec. Got it in my GitHub. So I think it's my gists. Oops. See all my gists. Painful. Sorry, let me go back. So, alright, so that's the RFC here. This defines TLS. Probably looks a little bit difficult to read. So AES-GCM. Initialization vector. There we go. Protecting plain text with strong key. Non-replayability is provided by using a separate nonce for each record, which with the nonce being derived from the record sequence number, with the sequence number being maintained independently on both sides. Thus records delivered out of order result in deprotection failures. In order to prevent mass cryptanalysis when the same plaintext different users, nonce is formed by mixing the sequence number with a secret per connection initialization vector derived along with the traffic keys. BT16. That's a bit annoying. Not sure I need this. Interesting. So post handshake. So handshake obviously I'm getting way ahead of myself because I'm only interested in, I'm sort of building this all towards building a full TLS stack. And so that's why I'm kind of getting into the weeds a little bit here. And so really, you know, I'm just going to focus on finishing the GCM implementation of AES. But then I'd love to know how it all fits together, because especially if the initialization vector needs to be unique. And I just want to know how that, you know, given that there's a set number, like there's a set size that you can use for tag and IV. I'd like to know how TLS does that, because I'm going to be building TLS 1.3 at some point eventually. So that's curious. Yeah. Because I would have assumed, because during the handshake, oh, here we go, vectors. So during the handshake, that's where you effectively derive the secret key, and we'd do that with Diffie-Hellman. It's interesting though. What did this guy say? So IV 12 bytes. The IV is generally prefixed to the ciphertext or calculated using some kind of nonce. Size of the IV should be defined by the protocol, right? So the protocol being TLS, so it should be quite clear. And then the tag should be 16. Should always be 16 bytes, but you know, maybe less. So 128 or less. In which case you need to know how many of the leftmost bits to pull out. What's this special publication? It's this thing. Okay, well, that's what I've got, I think. Isn't it? Yeah, that's what I'm building. Oh well, anyway, I'm getting way sidetracked now. But yeah, it's interesting, isn't it? Wow. So anyway, back to reality. Look at the GCM implementation. Somehow we'll have tag length known ahead of time, presumably. It has to be. Yeah, and anyway, and so when we do the authenticated encryption part, there are things that are expected to be known, and I feel like I haven't got that 100% right yet. So supported tag length associated with the key, so that has to be passed somehow. Definitions of supported input output lengths, whatever that means. Whose length? Initialization vector. Yeah. So I mean, we could do a check in here where we use IV. And pad. So the pad IV bit. So our example was the IV was, what was it? 12 bytes. So 96. Okay. And the tag, so we don't, yeah, I mean, the tag is obviously 120, what is it, 15, so 120 bits, but there's nothing in here that says, you know, this thing will need to return a tag, and we just don't know how long that tag needs to be. So that's the bit missing associated with the key. Unclear. I think we'll need some kind of, either we'll parameterize it, or we'll need to, it'll need to be, I guess we should parameterize it, right? Let's just do, I don't know, for one of the, I actually don't know if we need this, but let's do tag length. And we could be a lot more, we're a lot more particular about this. We could set up a different type, enumeration type or something. Yeah, not clear. Do we need this? Do we need tag length parameterized or not? Not sure. In which case now that should break. Why didn't that break? Ah, because I did it on the wrong function again. Where is it? Decrypt. Yeah, I don't know. Probably should build like a tag struct or something. Tag bits. Or tag length in bits. Tag bit length. So let's just say it's 120. Yeah, 8 times 15. Cool. All right. Yeah, it's not clear. Oh, I'll call it just tag length. In bits though. Bits. Cool. All right, I think I'm going to end it there, guys. My brain's tired. So what I'll do is I mean, we still achieved a fair bit. Let's have a look. So what do? We changed a couple of files, cargo, toml and main. If we look at what we added here, what have we got? Yeah. Just sort of built out the superstructure, added a test which fails. It's slow going, isn't it? But better than nothing. We're learning as we go. If I do, I'll just add this stuff in. Oh. CD. Git. And then we'll just say added, just call it fleshed out GCM AE algorithm and helper functions. Cool. And then tomorrow, what we'll do is we'll get into, well, we'll have to build out these helper functions. That's clear. And then we'll probably make a good go at GCTR, I think. And then by then we should be able to build sort of the guts of the main authenticated encryption function, and then we should be able to actually start running tests that, well, we should expect tests to fail for a while, but these things should give us information now about our implementation. So I think we're about a day or two away from tests that actually work or actually mean something. Yeah, anyway, and as usual, I'm putting it all in GitHub, so you can just go and have a look at my GitHub repo. GitHub snarky boojum. It's all in this GitHub repo at the moment called AES-GCM. 10 commits, very slow going. That's all right, we'll get there eventually. So you can see what we've built so far. It's pretty messy, lots of to-dos, not well documented. And I'm going slow. And it's partly because I want to really try and sort of make sure I understand what's going on, but clearly not mathematically. Anyway, so enough of that. Hopefully that's been enjoyable. Come back and watch me tomorrow. See you all later. Thanks for joining.